Hi, everyone. So I wanted to mention about using Lorentz transformations in interval form. So let's say there's an event. Let's say there is an event 1, and it takes place at some coordinate and time. So the Lorentz transformation can be written as gamma x1 minus vt1. And let's say there is an event 2. And again, we can relate coordinates and time of that event in between the two frames, right? So the Lorentz transformations reads like this. And remember, when we write down Lorentz transformations like this, it was implicit assumed that when the two coordinate origins coincide, you set the clocks at the origins to 0. So that sets the origin of time for a problem. Now we can subtract, right? So I can say that delta x prime equals x2 prime minus x1 prime, delta x equals, x2 minus x1, delta t prime equals t2 prime minus t1 prime, and delta t equals t2 minus t1. And so I can subtract the first equation from the second, and that will give me delta x prime equals gamma delta x minus v delta t. So if you have a pair of events, event 1, event 2, it is convenient to use Lorentz transformations in this difference form. And when you do that, you don't have to worry about synchronizing clocks at the origin when the origins pass each other. You just have a pair of events, event 1, event 2, and you can apply Lorentz transformation and delta form to that scenario, right? So the resulting Lorentz transformations will basically look the same, right? So let me write down Lorentz transformations for intervals of space and time. They basically look the same, but let me write them down for completeness. So this is forward, and then there is the reverse. Okay, so let's look at a problem. Let's look at a simple example which elucidates the use of these kinds of formulas. So let's say, so here's the ground. Again, folks, remember, there's nothing special about the ground, okay? Really, when we solve relativity problems, really the scenario is frame A and frame B. Frame A can be one spaceship, frame B can be another spaceship. It's just that we're so used to standing with our feet on the ground that I'm using that scenario often, for example, so you can visualize it better. But remember, there is no such thing as a special reference frame or absolute reference frame. So be very careful with that. So let's say the frame of the ground, or the frame attached to the Earth's ground, is S. And let's say there is also some kind of a spaceship that's traveling with speed v relative to this frame. And I'm going to call this frame S prime, the usual scenario. And let's say that there are 2 lightning strikes. Okay, so you have lightning strike 1, creates a little crater here. And later, 1/10 of a second later, there's a lightning strike 2, boom. And let's say that this is 1,000 meters apart, 1 kilometer. And so, okay, so this, so this is, and they're also 0.1 second apart. So delta x equals 1 meter and delta t equals 0.1 second. So this differences in coordinates are differences in the coordinates of the system S, right? The coordinate system attached to the ground. And so I might want to ask a question according to frame S prime, what is delta t prime? Okay, what is the difference in the time in the spaceship's clocks? And so we can apply, for instance, this. The problem has been presented to you in a way that you can just directly apply the second Lorentz transformation. I just want to illustrate their use. And so what you would say is, you would say, first of all, well, okay, so let me compute gamma. So gamma factor, if you plug in the numbers, it turns out to be 1.1547, okay? Okay, with that in mind, you could just say delta t prime equals 1.1547. I'm not going to put the units, but you should. It's a good practice. But for now, I want to sweep the units under the rug. 3 times 10 to the 8. So I factored out, I guess what I forgot to write down is that v equals 0.5 c. Okay, so the speed of the spaceship is 0.5 c. I gave you delta x, delta t, and I computed the gamma. Okay, so that's for v equals 0.5 c. Sorry, I forgot to say that. Okay, so this is, folks, you really probably have no idea just how much I want to make these lectures perfect and how much I suffer when that doesn't happen. So if I make a slip up, I'm sorry about it. And sometimes I re-record these lectures multiple times until I get it perfect. And it's still not perfect. So I planned it out and I slipped up and I beat myself up for that. So I hope you at least understand that, okay? So let me put in the 1,000 meters. 1,000 meters. So this is my delta x. You see this right here. And then I add the delta t plus 0.1 second delta t. And when all the dust settles, this comes out to be 0.115 seconds. So notice something interesting. First of all, in this example, the time according to spaceship's clocks is larger than the time according to the Earth's clocks. So I like this example because it offers me the opportunity to reiterate that point once again. This is not the scenario for time dilation. Time dilation refers to tracking a particular clock located at, when you have a particular clock, that means that clock is located at the same location in the coordinate system attached to that clock. That's really what we mean by tracking a clock, right? Clock is always at rest in its own reference frame. And so when you track a particular clock, a particular moving clock, you will always find that while that clock has ticked off 1 unit, your clocks will have ticked off more than 1 unit. That is time dilation. It's not some curious special case. It's a very important special case. In this particular example, the two events, lightning strike 1 and lightning strike 2, do not take place at the same location in either frame. So it is not obvious that it is not obvious a priori until you calculate in which frame the time interval between the lightning strikes will be deemed longer. Okay, so this is not time dilation, right? Okay, so the two events, note, the two events do not take place at the same location in either frame. This is not a time dilation scenario. Put another way, the two events are separated by space and by time in both frames. They're separated by different amount of space and different amount of time in two frames. In time dilation, the two events are separated only by time in one frame, but by a combination of space and time in another frame. In this problem, they're separated by different amounts of space and different amount of time in different frames. Well, since we're at it, let's calculate delta x prime. Right, so I'm using this as an opportunity to bring up some common misconceptions. One of the things that students commonly really love doing is taking time dilation formula and just running with it. You can't do that. It only applies to situations when two events are taking place at the same location, one frame. And that is what we really mean by time dilation, because that corresponds to tracking a particular clock. And while the clock actually ticks off 1 unit, other observers will say, no, our clocks ticked off more than 1 unit. So it's a very special, it's an important effect, but it doesn't describe all the situations. So I'm going in circles because this is very important. Okay, so while we're at it, let's compute delta x prime. Delta x prime, 1.1547. So I'm now using this formula, okay? Delta x minus v delta t. Okay, so this is going to be 1,000 meters. So this is your delta x minus 0.5 times 3 times 10 to the 8 over 0.1. Sorry, my mistake. What I meant to say is this. So this is V and 0.1. So this is delta T. Okay, I got my mistake. And when this is said and done, we get minus 1.73 times 10 to the 7 meters. So two questions that I have to you. One, why is it minus? And why is it so darn large? The two events were separated by only 1 kilometer, 1,000 meters, 10 to the 3 meters. But now they're separated by this humongous number, 10 to the 7 meters. Why? Pause the recording, think about it, and then resume. So here's the answer. This is not a relativistic effect. Notice the only way that this formula right here differs from the Galilean transformation is in the factor gamma. And the factor gamma is not large. It's only 1.15, very close to 1. Other than that, it's exactly the same as Galilean transformation. So this is not a relativistic effect. So physically, why is it so large? Well, we discussed this in our discussion sessions in the first week, right? So you have lightning strike 1. Let's say the car was here at that position. And then later you have lightning strike 2. Here's the second lightning strike. By the time the second lightning strike has hit the ground, the car is way over there. Well, in this case, it's a spaceship, okay? It has traveled humongous distance. It's past the moon. Right, so here's the coordinate system S prime attached to the spaceship, or in this case, to the car. And so the second event happens way in the rear view mirror, right? You see here's x prime equals 0. Here's x prime equals 0. The second lightning strike happens at x2 prime way, way less than 0 in the rear view mirror. So that's the fact that it's in the rear view mirror is why you get this negative sign. It's at negative x prime. Okay, so here is x prime bigger than 0, and here's x prime less than 0 at that instant when that second lightning strike is hit. The spaceship is located at that position at that instant. And the reason it's so large is because the car is moving so fast, or the spaceship is moving so fast. Mathematically, it's this v that's making it large. Physically, just the car has moved so far. Okay, it's way over there. So the negative aspect of the negativity of this and the fact that it's so large, it's a trivial effect. It's not special relativity. It's just the fact that it's a moving coordinate relative to the ground, and the coordinate has moved really far. Okay. I want to call your attention to a couple of important points here. This delta x is not a length of an object. So remember I said that the lightning strikes, they make craters. So there's a physical segment. You could lay out a rod of length 1,000 meters here in between the craters. The length of that rod is 1,000 meters as seen from the ground. The length of that rod is even less than 1,000 meters when calculated using our system of rulers and clocks in the spaceship's coordinates. So clearly this is not the length of that rod. Okay, so this is the difference of coordinates of the two events, two lightning strikes, i.e., it's a distance between locations of the two events in system S prime. It is a distance, but it's not a length of an object. It's the distance between locations of the two events. So close your eyes, imagine you're in this car, this spaceship. When lightning strike 1 happens, you happen to pass right over it. It happens at your x prime equals 0, right behind your trunk. And then you've moved really far away. You look in the rear view mirror. The second event happens when it's way, way back. And so in your coordinate system, the difference between coordinates of these two events is very large. So why is there this strange subtlety between the length of an object and the length of an object not being equal to delta x, or delta x prime? Sorry, it's not equal to the coordinate difference. So if I have an object that's stationary relative to me, how can I compute its length? Well, I can lay out a ruler. I can place it next to the ruler. It doesn't have to be, one end doesn't have to be at the origin. And I just look at the difference of tick marks on the ruler, right? I can subtract the coordinates of two ends. When this object is at rest relative to me, I can calculate the first coordinate, go have dinner, come back, calculate the second coordinate, and then do the subtraction. But if you want to measure the length of a moving object, you don't often think about this, right? We don't often think about how to compute the length of a moving object, but it's a non-relativistic idea. It's just an everyday idea. If you want to measure the length of a moving object by the method of the difference of two coordinates, you better measure those coordinates simultaneously. For example, by taking a picture. That's what really measuring simultaneously means. Imagine if I perform that measurement not simultaneously. I'm just trying to make sure that you can see this. It doesn't help. Let's see if this doesn't help. So I have an object, right? And I want to measure the length of this object by subtracting the two coordinates. Imagine if the object is moving. Imagine if at some moment of time I measured this coordinate, and then 10 minutes later I measured this coordinate. Obviously, I would get a humongous number, and that doesn't represent the length of the object. So to measure the length of a physical object, such as this rod in between the two craters, or to measure the distance between the two craters, one must to measure the length of an object, to measure the length of a physical object by subtracting the two coordinates of its ends, one must measure those coordinates simultaneously. But in this example, when we computed delta x prime, that's a difference of coordinates of two events that were not simultaneous. First, there was one lightning strike, then we waited a little bit, and then there was another lightning strike, and we recorded the coordinate of the second lightning strike. So I just wanted to use this as an opportunity to bring up to the forefront of your conscience this idea that for moving objects, difference in coordinates equals the length only when you measure those two coordinates at the same time, simultaneously. And in fact, you can see in these formulas for delta x or delta x prime that you do get the length contraction formula only when delta t equals 0, delta t prime equals 0. In that case, delta x prime really does correspond to the length, right? So if you perform the measurement simultaneously, so for example, if you look here, if you performed the measurement if you perform both measurements with delta t prime equals 0, you really do get delta x equals gamma over gamma times delta x prime, or delta x prime equals delta x over gamma. Gamma is larger than 1. Delta x prime comes up to be less than delta x, right? So if delta t prime was 0, you get delta x prime less than delta x, and that is the length contraction formula. Otherwise, it is not a length that you're talking about. It's a difference of two coordinates. And I think I should stop here. I think I made the points that I wanted to make, that you don't have to synchronize clocks at the origins, that if you have a pair of events, you can use Lorentz transformations in this delta forms, which look exactly like the original ones, just with deltas. And there's a reason for that, because the original ones really were also in delta forms. It's just that the first coordinate was x equals 0, x prime equals 0, t equals 0, t prime equals 0. When I use this to look at a simple problem, I use that as an opportunity to draw your attention to the fact that not everything is a time dilation. In this case, the two events happened at different locations in both frames. And so here you see that the time in the moving frame, in the frame that's other than yours, is larger. In a frame that's moving relative to you, that time difference is larger than in your frame. And then, well, at it, we also computed the delta x prime, which corresponds not to a length of some object, but to a difference of coordinates, which corresponds to the distance between locations of the two events. But it does not correspond to the contracted length of a segment between the two craters. And I use that as an opportunity to remind you that when you measure length of something by the method of the difference of two coordinates of the ends of that something, you better measure those coordinates at the same time. Otherwise, you're not really measuring the length of a moving object. Of course, if the object is stationary relative to you, then it doesn't matter that you perform the that you mark out the locations of the two ends simultaneously or not. Okay, I think this summarizes what I wanted to say. Thanks.